Hello, my name is Aarav Dugar.
Hi, I'm Rahul.
I'm Paarth, Jain.
I'm Saanvi, Suresh.
And I'm Gabe.
And our research project proposes a solution to potholes in smart cities environments. Our presentation will take you through the steps of our research project, all the way from the outline to the results.
Our presentation is based around the concept of a smart city. A smart city is an urban environment that collects data on itself in an effort to better city life. It increases efficiency, increases quality of life, and makes the city safer and more economical for its residents. Over to Aarav now to explain how we integrated the concept of the smart city into our project.
We chose to solve potholes because they inhibit the abilities of roads in a multitude of ways, as well as being a large nuisance. I'm sure everyone here that drives can relate to the feeling of hitting a large pothole. Aside from that, potholes have significant negative effects by increasing emissions, creating bottlenecks, diminishing productivity, and causing a lot of accidents. This problem is only getting worse. With this in mind, the purpose of our project is to develop a 2D LIDAR-based system to efficiently locate potholes, accurately calculate their volume, and precisely fill them. The goal was to develop a small-scale prototype to test the viability of this.
In order to locate potholes, we're implementing a technology called LIDAR. LIDAR is short for light detection and ranging, and simply put, it works by the LIDAR sending out a beam of light or a laser, having that beam of light reflect off an object and returning back to the LIDAR. The return value for this is actually a time, but using something called a backscattering algorithm, this time is converted into a distance value, which represents the distance between the LIDAR and the object that is reflected off.
For our prototype goal, we wanted to design a 3D CAD model and create a small-scale, inexpensive prototype that could prove our concept could work in a smart city. So this is our detection module. We created a mount for the LiDAR using Lego Technic pieces so that it had an adjustable angle so that we could test both 30-degree angles and 45-degree angles to see which one would work best for our detection system.
As Saanvi mentioned, once the prototype detection module read the pothole, it went over to the dispenser module. The dispenser module stores and dispenses our pothole filling material. It contains a funnel and a servo, which is the yellow thing you see at the bottom of the screen on the left. Using that servo, the cap is able to spin, allowing the pothole dispensing material to fill the pothole.
If you refer to the presentation, you'll see our final prototype CAD models. On the left side is our detection module. This detection module was based off of a triangular prism. Basically, we chose this due to its sloped side as well as the other mountable sides. Not seen in this is our CAD model for our Raspberry Pi. The Raspberry Pi was in charge of controlling the inputs and the outputs of the LiDAR. Specifically, we mounted the LiDAR on the slope side of the triangular prism in order to create an artificial angle which would allow the LiDAR to create a 2D map and change it into a 3D map, which we'll discuss later. And on the right side of the presentation is our dispenser module. We utilized a Creality Ender 3 V2 3D printer due to its ease of use as well as its accessibility. Mainly, we used a horizontal gantry in the 3D printer in order to lock vertical movement while ensuring horizontal movement worked exactly as we planned.
For our pothole detection module, we implemented 3 algorithms: adaptive breakpoint detection, iterative endpoint fit, and gradient comparison. Adaptive breakpoint detection organizes our data into curves by identifying corners or vertices. For instance, take a 6-sided dice. This algorithm would partition that die into 6 sections based on the vertices. Next, iterative endpoint fit is applied to simplify our data by approximating these curves with fewer points, allowing us to do real-time detection. Finally, if a significant deviation in slope is observed between these segments, then a pothole is detected. To test the viability of these algorithms, we conducted over 150 trials with simulated potholes of small, medium, and large size depicted on the slideshow, alongside different parameters for our LiDAR instance angle mount and our slope deviation threshold. This involved mounting our LiDAR module at 9 inches high and gently pushing it to capture the entire scope of the pothole. Here I will hand it off to Rahul to discuss the volume aspect of this project.
Just like Aarav mentioned, once we detected the pothole, we were able to get the volume of the pothole. How we did this is that the LiDAR sensor would be in constant motion at a roughly constant velocity on a car or on the vehicle that we would be mounting it to. From there, we can generate hundreds of angled planes per second and use trigonometry to essentially get them out to a 3D map, essentially combining hundreds of 2D planes into one 3D plane. From there, we can use a mathematical concept called a convex hull, which will fit a figure to a set of 3D points, as you can see on the left right there. Once that's done, we can use some more complex math, like the polyhedron volume formula, to get the volume of the sensor, to get the volume of the hull, thereby giving us accurate volume detection.
Additionally, we collected data on our false positive percentage. which reflects the probability that our system incorrectly identifies a crack or irregularity as a pothole. After conducting trials in 20 cracks, we determined our false positive percentage to be just under 20%. Our testing confirmed the efficiency and effectiveness of our pothole detection module. With the best parameters, we determined that we could achieve detection rates in the high 90% in the pothole percentile.
Now on to volume analysis. Like I said before, once a pothole is detected, the volume analysis is a completely separate thing. Therefore, the threshold value doesn't really matter for volume analysis. What really matters is the size of the pothole and the angle of the mount. Here, as you can see, we tested 30 and 45 degrees with 3 sizes of potholes. The 30 degrees was significantly worse at about a 26% error rate when compared to the 45 degree, which is about an 18% error rate. And this was tested across small, medium, and large simulated potholes. Now on to our best parameters. Using the data that we collected earlier, we got a set of best parameters to use. We chose an angle of 45 degrees, mainly for its low volume percent error, which we attribute to the fact that the 45 degree mount could see deeper into the depths of the pothole and thereby giving us more cohesive map. We chose a threshold value of 2.5 instead of the 1.5, even though both technically gave 100% detection rate when given a pothole. However, with 1.5, the false positive rate would be much, much higher. So instead, we chose 2.5 as the false positive rate was lower at about 20%. This accumulates into an average accuracy of 90% for both when a pothole is detected and including false positives, for an average volume percent error of about 18.41%.
Our method has highlighted 2 limitations. First being human error. During our method, we had to manually push our LIDAR instead of having a constant velocity. This meant that our volume was not completely accurate and diminished our percentage by quite a few. Moreover, our LIDAR rotations per minute was maxed out at almost 400 rotations per minute. This means that we were able to take about 400 scans in a minute. And with a larger RPM, we would have been able to take more detailed image of our volume, therefore creating more accurate volume estimation.
Finally, our prototype results. As we spoke about earlier, our prototype has 2 different components, the gantry and the dispensing module. On the left of your screen, you can see that the prototype worked in real life. We mounted our funnel to an Ender V3 Pro, and as you can see in the animation on the right, it was able to conduct 2 points of movement. The cap was able to be spun by the servo, essentially allowing us to dispense our pothole filling material, and it was able to move left and right on the horizontal gantry.
For our major findings, we found that the 2D LiDAR was indeed most efficient for this project, rather than the 3D LiDAR, which is too expensive, and machine learning. We also learned that a prototype can be implemented into a smart city, and I will.
The significance of our findings are extremely broad. Within road management, we believe we can save about 1.4% of deaths on roads, save people over $137 billion on car maintenance and fuel costs, and save the government over $177 billion on road maintenance costs for a potential 7-year increase in road length. Outside of road management, our novel geometry reconstruction algorithm and volume estimation can be used in a variety of different fields. From scanning the oceans to medical imaging, we believe that this will make geometry reconstruction and volume estimation much more cost effective for the average person.
Once we confirmed that our prototype worked, we developed a larger scale implementation plan. As you can see on the right of your screen, we redeveloped our prototype CAD model into a much larger. The rail you see is about 6 feet long and is able to encompass a normal US lane. That rail will be mounted to a city sweeper. A city sweeper is a vehicle that traverses urban environments frequently, cleaning the streets, and it was the perfect vehicle for us to mount our system. It moves at a slow speed, only about 10 to 15 miles an hour, meaning we won't have to stop to fill the pothole. Moreover, it has the cleaning brushes already, as one of the necessary components for us was having to clean out the pothole before putting in the filling material that Rahul was about to talk about.
Thank you.
To implement the city sweeper into a smart city, the city sweeper will travel autonomously throughout the city, detecting potholes and filling. It will also take data from the potholes, its volume, where it is, and upload it to road management services so that they can see which roads in the city have more liabilities and need to be fixed.
Like Paarth mentioned earlier, we had specific things that we needed out of our filament table, and thus we chose instant asphalt, otherwise known as cold patch asphalt. unlike regular asphalt, it doesn't need to be hot, it doesn't need to be liquid, and most importantly, most of the time we don't need to close down the roads in order to dispense it. Instant asphalt is instantaneously ready for traffic and it's optimized for flow out of the funnel. So it should almost instantly be ready for basically anything and traffic almost immediately.
Our research process has helped us identify two future directions. Firstly, being implementing accelerometer. Accelerometer will ensure that we do not need to rely on constant velocity and will adjust to it in real time. This will ensure that our volume detection and detection is much more accurate. Also, we will implement vertical movement. This will allow us to move in more of a 2D way, and also it will help us optimize certain performances and functions for the LIDAR by adjusting the angle at any given moment. Finally, it will also help us account for the time delay between the time it takes for the LIDAR to detect it, and as well as the length of the sweeper truck, and then finally dispensing the system, the instant asphalt.
So we couldn't have done this alone, so I'd like to acknowledge a few people. Our project mentors, Benjamin Lee, Alexander Cho, and Tiffany Powell. Our project RTA, Adam Bathurst. Our research coordinator, Ashi Mishra, and the director of GSET, John Patrick.
We would also like to thank the Rutgers School of Engineering, Lockheed Martin, the GSET scholars, and the GSET RTAs for their continued support.
These are references. Thank you. Any questions?
What was the most difficult aspect of the project?
So I would say that the most difficult aspect in terms of the prototype development, which I guess I'll let Paarth do a bit later, but for us personally, we worked on this prep module, me and Aarav. So with that, it was mainly getting the LiDAR sensor to actually do accurate reconstruction and making sure we had all those things in properly, which again, we showed in our results. And would Paarth like to talk about the prototype?
Yeah, so one of the challenges with the prototype was that the cold patch asphalt or whatever filling material is fairly heavy. So we had to design a system that could hold it up using just that small little cover. And we also had to design a system that would dispense the material really quickly. And so those two challenges were pretty difficult, and they came out pretty well, and we're pretty happy with it.
Yeah, so you were talking about how you use instant asphalt to fill in potholes. Is there, like, because of how quick it is and, like, the efficient way to do it, is it, like, have lower longevity than normal asphalt?
So yeah, instant asphalt does have a lower longevity. It's more a temporary solution, but the idea by filling with instant asphalt is that the road maintenance becomes regular. When you fill with normal asphalt that has to be heated, it's very rare that cities will go out and refill those potholes or maintain the roads. But with instant asphalt, because it's just regular road maintenance, we're able to increase the lifespan by a lot longer and still cut costs economically.
Yeah, so basically what one statistic we found in our research was that road maintenance costs around $177 billion. And implementing a solution such as this would actually increase road life by about 7-ish years and decrease the $177 billion cost.
What is the fastest that a car, like you said you were bouncing off like in the car, right? What is the fastest that it could be traveling for, like at the current rotation per minute, so like have an accurate reading and like produce asphalt?
Yeah, so obviously this was a prototype. Our sensor spins about 400 RPM. The fastest speed that you can go above that is about 6 miles an hour, which isn't very good. A slightly better sensor can go up to 2,000, 40,000 RPM, which can get you well past the 15-mile range. And future sensors, as in the essentially stuff that attach a better motor to it, can do anywhere between 10,000 to 20,000 RPM, which will get us well past the 15-mile-an-hour range.
Is there any limitation to the size of the potholes that you have tested? Like, is the pothole too large or too small to be filled?
So basically, there's really no limitation at our point. The only limitation is obviously our prototype. It's small scale, so basically it mainly depends on scaling. So as Paarth was talking about earlier, we have one that can fit a whole 6-foot US lane. And so basically, another limitation of that would just be the amount of instant asphalt we can store in a city sweeper. But as you saw back in the CAD model, there's a lot of room in the back, so one future implementation for this is just storing instant asphalt. We create more of a funnel system to just have more storage for this instant asphalt. So technically speaking, there is no limit as long as because it can traverse an entire lane, and the only limit is just as much as you can fit in a sweeper truck.
All right, that is all the time we have for questions. So